Uh, Welcome everyone to this lecture session on digital circuits design using VHDL, and it's a very important lecture, and it's very relevant to courses like digital system design, microelectronics, microprocessors, mixed signal design, or you name it. And what's the reason behind that? That this thing is so common to design different type of system is because of the flexibility, the cost effectiveness, efficiency in using these. We call them as HDLs, like hardware description languages, in achieving a simple digital circuits design, or in mixed signal designs as well. But primarily we used HDLs, and in this case VHDL. I'm just going to give you a brief introduction to that how we can design digital circuits using VHDL. Okay, so let's carry on with our session. So as I mentioned in the previous slides, that HDL stands for Hardware Description Languages, and this summary is for the course is very specific to digital hardware design or advanced digital hardware design. But I think most of the students listening to this lecture session has kind of a well introduction of some of the topics mentioned here. But we will, since as I said, we are covering the basic introduction on how to use an HDL, in this case VHDL, for a digital circuit design. So we are not going to cover everything in this lecture session or in the course. Again, simply a basic introduction on how we can design a simple basic digital circuit using VHDL. So let's carry on with this. So basically, again, relevant to basic or advanced digital design course, these are the two very popular hardware description languages, VHDL and Verilog. So even just simply knowing these keywords and what they do is a very powerful knowledge information for everyone. Okay, so let's carry on. So what is VHDL? So VHDL is an acronym for very high speed integrated circuit. But the way I see it is it's a very high speed digital language. Okay, that's what it is, and it's a digital design language. But historically it was called as description language, and turns on to be very high speed integrated circuits, and initially by Department of Defense and so on and so forth. It primarily the IEEE organization, of famous engineering organization developing standards. So in 87 it built a standard for that and called this the number or the standard relating to HDLs. Okay. By no means I want you to understand this everything or remember this everything, but knowing the historical perspective of anything you're trying to learn is very powerful, as you've been told numerous times in the past during our lecture sessions or lab sessions. Okay, let's carry on. So what HDL does, that for example, historically, if we need to design this digital circuit, so what we do, we go ahead and find an OR gate IC and an AND gate IC, and because there is a bubble here, if there is an IC which can provide us this kind of a bubble, means inversion. I think most of the students already know it. So bubble means inverter. It will invert. So if the AND IC has the kind of a feature, then only two ICs are required. But if not, if we only can find a simple AND IC with no inversion, then we need an inverter. So we need 3 ICs, and then we're going to use, for the prototyping, we are going to use the breadboard, the wires, power up the circuit, and make sure that we are getting these timing diagrams. So what an HDL or VHDL does, you can design this circuit using the language, and you can test the waveforms, the behavior of this circuit, in a graphical view. And this is what I'm going to show you, that how we can do that. So let's carry on. So here, like any other system, in this case digital system, we have inputs and outputs. So this is the digital system we're trying to implement. So just to get started with the most simplistic one, so we want to implement an inverter. So this is the symbol of an inverter, as everyone knows. And how we can do that using VHDL, and this is this is how we implement it using VHDL. So what is an entity? So an entity is this block. This digital system block in VHDL terminology, or even in Verilog terminology, is called an entity. Okay, I think in Verilog it's called component, but anyhow, so entity or component means this particular block, which is basically has multiple inputs, multiple outputs. As you already know, I've told you, if you see a slash in there or any signal in a digital design, it means it's carrying multiple signals. So multiple inputs, multiple outputs. So since we are trying to implement this inverter gate, so we are defining the ports. So again, we are defining the ports. So the port is that it has one input. So I'm defining A as an input, which is a bit. So it's just simply 1 bit signal. And C, like say the C here is an output bit, signal. So remember this on the last line when you're defining the entity. So this is an entity, I name it as a NOT gate, and then I define the ports like this, and we end the entity with the same name, NOT gate. So remember the semicolons here, the lines, the last line in the ports when you're defining the entity does not have the semicolon. So please remember this is the most common error students do. And secondly, remember this semicolon, that we need a semicolon at the last parenthesis of the ports when we define the ports within an entity. Okay, so now we have defined the digital block. So this digital block of digital system is defined here as an entity. So the block is defined. Now we are going to implement its functionality. So the only thing what we did here, we defined inputs and outputs as ports, and now we are going to implement the implementation. And implementation, the key word is architecture. So we are defining the architecture for this entity, and we say architecture, you can give any name you want. I'll just say arch_1 of NOT gate. So the architecture for NOT gate is, that's all the language norms you need to use for VHDL. Then you begin, and this statement is a very, I think you have already done a lot of programming in this course, and you might have done in prior courses. Is a simple programming statement that whatever the signal A is, invert it. NOT means inversion operation, just like this. So if it's 0, make it 1. If it's 1, make it 0, and assign it to the signal C. So again, taking the input A, inverting it, and assigning it to the output C. So we have implemented the desired architecture for NOT gate and for this digital system. Very simple example that how we do that. Okay, so we are going to practice it, but let's carry on for now. So now we have in the last slide what we have done, we have made the entity, we implemented its functionality in the architecture, but the question is how I am going to test my design. So this is so how I'm going to test my design is the answer. So this is what the block we defined as we started with the previous slide, that we have an input A and an output as a C. This is our digital system, which is nothing more than an inverter. So how we are going to test it? For that, we implement or write what we call it as test bench. And in this test bench, again, it's if you see this, the test bench is kind of an entity like a block, but it doesn't have any ports. Okay, so no ports, but if required, yeah, it can have ports as well, but that's not the case. We just want to test this particular block, so no entity ports for the test bench. And again, we are defining the architecture, name it anything you like, but I'm calling it as test cases of test benches. And here what we do, so we bring this block or this entire entity into the test bench as component. So we'll say component, you see the name is same as the name of the file or the entity called not_gate and is, and we just, the only thing, what if you just cut and paste the entire thing here, and you see we are replacing the word entity with component. And the end line is a bit different because it will be end component rather than end NOT gate. So it's very simple to understand what we are doing here. We are bringing the block defined in the main file as a component into the test bench, and now here we are going to test the functionality of the component. Okay, to test the functionality, these are internal signals to the component. So how you're going to how the test bench wants to connect to these signals. So we define internal signals. So I gave them the same name as A and C, but you can make it any name you want. Okay, you can make it, as I said, one letter name or multiple letter names, as long as the names you define are within the context of the VHDL norms. You can have any name you want, but these are the internal signals to the test bench. These signals have nothing to do with the component. So now we begin, and now we create an instant. We create an instant by using this statement. So an instant in memory, you can say, or instant in the FPGA fabric. So what we are doing, we are creating DUT stands for design under test. Okay, but it can be any name, just like it can be any name here. Okay, and you see that we take this NOT gate, so we are creating an instance for NOT gate, and the port mat for that instance is that we are connecting A, this signal A, with the internal signal of NOT gate. This signal C connecting with the internal signal for the component C. Okay, so now if everything is typed correctly, done correctly, it means what you done, that you used these components and made it kind of an active in the design. Okay, so that's part of the classes or structures what we have discussed. You make your class or structure as in this case it's an entity, but in programming terms we already discussed that, and then you instantiate that particular class or structure. Here we are instantiating the component which brought into the test bench, and now we are going to test the component. And what we do is for that we use or make a process. A process is like a function in VHDL. A process with no parameters, as you can see here. Also, there can be processes with have parameters, and you begin and you start with A is equal to 0. Okay, wait for 1 nanosecond, it's a kind of a delay, then make A as 1, wait another 1 nanosecond, and it will be kept on going depending on the how much time you want the test bench to run. Okay, so this is descriptive kind of the detail of how the test bench is written or gets written in VHDL, but in graphical form, that's what it is. So what we did, we implemented this entire thing, the test bench, as a block. We brought this entity as a component. We defined internal signals to the test bench as A and C, and we connected these together. That's all what we did. And in order to practice it, we use it's a free tool called edaplayground.com. So I would like you to go to that site, and I'll myself go there. Just give me a minute. I'm going to escape from here, and here's the EDA playground. And as you can see here, the NOT gate is already typed in here. The test bench is all as I described you is typed in here. So what you're going to do, just make up a free account, and some of the settings, simple settings are that you will see once you do your account, you will see this on the left menu bar like this. So in the languages and settings, make sure you select VHDL. Okay, but see the power, you can practice a lot. System Verilog, and it's a very powerful site. So you select under VHDL, and then again, important thing, in the top entity, put the name of your test bench. So in this case, we are just using test bench, so it has to be test bench. And under tools and simulators, make sure you check open EP wave after run to see the waveform. So again, 3 settings. Again, I'm going to go back. So setting number 1 is you select this as VHDL. Setting number 2 is you type here, because you're running it for the first time, the top entity, it will be blank here, so you have to write the name of the test bench here. And the third in, you click and enable or put a check mark beside open EP wave after run. So I'm going to run it. So what happens is if you're running it for the first time, you may have to click multiple times or refresh the page. I found it very but again, it's a free tool. And the second thing, what you see in there is that you might see multiple signals just like this. You just simply do this, and sometimes you might see that there are no signals here, so you just click on get signals and click on the test bench, and you can select all the signals, append all, or you can select the number of signals you want to see in this particular timing diagram. So here's your time, okay, time in picoseconds going on. As you can see here, this simulation is running from 0 to 2000 picoseconds. So when A is 0, C is 1. So that's what you can see here. And when A is 1, C is 0. Okay. So if you click on, so here it's 0, 1, and if you click here, it's 1, 0. So total inversion, and that's what we wanted to achieve in our design. So let's carry on. So that's another kind of a good practice for that we want to implement this design. So the entity, the VHDL entity for that can look like this, but for this particular course, I rather suggest not to use these libraries, because you can implement just like this as you did, but rather than using standard logic, just simply use bit as we did in our previous example. So just use bit rather than standard logic here, and you just comment out this particular line. And to comment out in VHDL, you use 2 dashes, okay, like a head, 2 dash you use, and this is how you comment a line in VHDL. Okay, so just use this as in bit out bit, and they gave it a funny name, but anyhow you can put anything that you like. And as you can see here, so the entire circuit is implemented by just one line. Okay, and it will be a good practice for you to write its test bench. So what I have done in relating to, because this circuit is using multiple gates like an AND gate or NOT gate, so I have another example which I can show you on EDA Playground. And in here it's called multiple gates. So VHDL multiple gates, and I want all of you to practice this. As you can see here, I define my entity. So let's go in here, and here's my entity. I'm just going to, so that you can see that, you can pause the video and type in everything what you see in here. So it's basically just implementing again the NOT, the AND, the NAND, OR, NOR, exclusive OR, exclusive NOR, or just another function, a digital function, and has multiple outputs going to the respective port signal on the entity. So go ahead and please type everything by pausing the video. And once you are done with this, you come to the test bench, and here's the test bench, and I'm going to very slowly go down. But as you can see here, we're just bringing this entity as a component in here. Okay, and then we instantiate the component. So this is the instantiating the respective signals defined in there, and as you can see, everything is defining as a bit. And then you go into the process and provide your input conditions. So there is only two inputs, and based on those two inputs, the functionality behavior is monitored. And once you do that, and things are up and running, you just simply just run it. So if there are errors, you make sure that you fix the errors. So see, waves are loaded, but in this case, good example, I'm going to get the signals, go to the test bench, and I will say these are my inputs, because I just want to arrange it. So these are my inputs, and I want to see my AND as an output. So I will say append selected. So as you can see here, then I have a buff, append selected. As an inverter, append selected, then a NAND, then a NOR, and the rest of it. Okay. So as you can see here, you click here, 0, 0, so AND gate, the output will only be 1 when both are 1. So if I click here, as you can see here, and it's very easy for you to analyze the timing diagram and make sure that it's the design that you have implemented is working the way you intended it to work. Okay, so that's another good example. You can minimize it. This will basically reduce the number that you have to run it again and again. So rather than closing it, just minimize this window, do whatever changes you need to make. Even if you need to make a new design, just keep this window minimized, and hopefully it will run and it will show you the waveforms the first time you click run, in case there are no errors in your design. Okay, let's carry on here. So as mentioned here, so please do this design as well. It's a good practice and kind of a learning for all the students. So now I'm just going to give a brief summary on the HDLs. I think it's a very good read. HDLs are extremely important tools for modern digital designers. Once you have learned HDL or via Verilog or HDL, you'll be able to specify digital systems much faster than if you have to draw the complete schematics. The debug cycles often much faster because modifications require code changes instead of. So I think these are pretty common uh, things which I have already mentioned in this lecture session. So, but please go ahead and read it, and if you have any questions or concerns, ask it during lab time, lecture time, or office hours. Okay, so keep learning and never stop learning. See you in the next session. Take care.